Hi folks, welcome back again. Gonna talk a little bit more about what we can do with mixed models. In particular, gonna talk about what are called nested designs or a nested ANOVA. Again, as I've said before, it's a linear model, and we're probably going to use some semblance of an analysis of variance to analyze that model. But it's going to be similar to what we were doing when we were playing around with random effects before with a mixed model, in that we're going to want to keep track of the error structure, and we're going to want to put some structure to the error term for the purposes of both how we're going to estimate our parameters and doing our hypothesis testing. And so I've uploaded some data, and before we talk about exactly what a nested design is, let's just look at data from a nested design. Make that as small as possible. Hide in the corner. And so here I have this object called seeds nested. So I can read that in, and we can take a look at that. Let's take a look at this. Okay, so what do we have here? The scenario with this kind of a design for this example is that there are 4 different populations that we're interested in, cleverly called Northville, Midville, Weston, and Easton. See what I did there? And what we'd like to know is we'd like to know whether or not the mass of a particular species of plant, whether or not the seed mass varies among these different populations that we've identified. And so from each population, we took 5 seeds from each of 5 families. And so this is what we mean by a nested design, because what do we have? So if I were to just look only at Northville here, okay, so within Northville, let's say that that's Northville. Okay, within Northville, we took 5 different families. So 1, 2, 3, 4, 5. Okay, so this is family A, B, C, D, and E. And then within each one of those, you can see here, so for family A, we have what? We have 5 different measures of seed mass. So we've taken 5 pieces of information from each family. And so here's our seed masses. Okay, and so this is what our experimental design is. And this is why it's called a nested analysis. So the 5 families are nested within Northville, and then likely the 5 replicates within each family are nested within family. So here we have 3 different hierarchical levels. We have the level of population, we have the level of family within population, and then we have the individuals within family. And likewise, if we look at our data here, you know, we go to Midville, and it similarly would have 5 families in it. Here the 5 families would be family F, G, E, F, G, H, I, and J. And then within each of those, we have 5 observations, and so on and so forth. Okay? And so the interesting thing about a nested design, and well, maybe not interesting, but certainly something you want to keep in mind, is paying very close attention to what your actual unit of replication is when thinking about estimating parameters and when doing hypothesis testing. And so if we're interested in the differences among towns, right, or among populations, we have 4 of them. We have Northville, Midville, and then we could, if we wanted to waste more time, do North or Easton and Weston. But it's that same setup, and what we're interested in is whether or not the populations are different from one another, which means that our unit of replication is actually the family. So even though we went through the effort of collecting 25 different pieces of information for Northville, in reality, we only have 5 independent observations, 5 random variables, because all of these nested within each of these families are not independent of one another. And so this is an important thing to always keep in mind, both when you're designing an experiment as well as when you're reading somebody else's experiment. I will say this is probably the most common error I've seen in the literature when I've been looking. And I don't think it's a malicious error, because as we'll see, the default on statistical programs doesn't take into account this nested nature. We're going to have to either do that by hand or use the appropriate syntax in R, which will do both. Okay, so hopefully it's clear exactly what a nested design is and why we need to keep track of the non-independence. So let's go ahead and make me small again. Make me disappear. Okay, and so let's start with making a bad model, because why not? So I'm going to call it a BM for bad model. And it's going to be a linear model where seed mass is going to be some function of population, because again, what I want to know is whether or not there are differences among populations. And then the data equals my ND there. So I go ahead and I run that. And now let's go ahead and let's load in that car package. Library car. Okay, and let's do an ANOVA on that. ANOVA, my bad model. And what do we have here? Ooh, it's significant. And again, this is often how people get themselves into trouble without paying attention to the nesting structure, because we know that there's only 5 observations in Northville, there's 5 observations in Midville, 5 observations in Weston, and 5 observations in Easton, which means at most we have 20 independent pieces of information. Okay, so we would start out with 20 degrees of freedom, and as soon as we estimate the mean, now we have 19 degrees of freedom, so on and so forth. But notice what the output here, because we didn't tell it to pay close attention to the structure, we have 96 degrees of freedom in the error term, which is clearly wrong, because the most we could possibly have would be 20, and that would be if we didn't even calculate the mean overall, right? There's only 20 independent pieces of information, yet our model is saying that that there's 100 pieces of information, which isn't right. And so we could try to fix this using the linear model function in R, and we could ask R ever so kindly to treat that as being nested. And we can do that by saying we want to include population in there because we're interested in the differences among population. But then what we're going to say is we're going to say that families are nested within population. And so how do we do that? We would say plus, and then I would say population, once again, population, and then I would say family. Okay, so this is the kind of code I could write it. This is the traditional older way of setting this up, both in R as well as other programs. And so if I go ahead and I run that, now let's do an ANOVA on that particular bad model. Okay, so now at least we're docking ourselves a little bit more degrees of freedom here in the denominator. Indeed, we have 4 populations, so we have exactly what? We have 4 populations, we have 3 degrees of freedom across populations, and then family nested within population, we have 16 degrees of freedom. That's because we started out with the total of 20 families, and we had 4 different populations. So there's 4 different means that we calculated, right? So it's the total number of degrees of freedom at that level minus the number of parameters estimated. We estimated 4 means, and so we have 16 degrees of freedom there, and then we have the residuals. Okay, so this is the part where the most frequent errors occur when people are analyzing these kind of models, because it looks like this model is working fine. Notice here that it's saying that it has these alias coefficients. It's just kind of giving you a warning. The reason why it's giving you the warning is because of how the dummy coding is working in the background. It's not falling apart, but it's just letting you know that not every family was in every population. And that makes sense. Family A is only in Northville. Family B is only in Northville. It can't be in both places. As a side note, if you are ever doing these kind of analyses, it's really important that each family gets its own unique name, because the computer, any kind of computer you use, if you recall, or if you name one of the families in Midville A, if it's always family A through E across these populations, the computer is not going to know that that family A is not the same as another family A from another population. So just make sure that you always have unique family identifiers for those things. Okay, so the reason why this is a very common error in the output here, if we look over here, is that the computer is always using the residual sums of squares as being the denominator. And so when it's calculating the F statistic. And so if we were to look at, say, how it's calculating this F statistic here, right, the 28.5 that's associated with population, what it's doing is, what do we need to do? We need the mean squared for 634.19. We need the mean squared for population, which is that. And then we're going to divide that by, and let's start with the total, right? The residual sums of squares. So that's what? That's 593.34, and then divide that by 80. That's where it's coming up with that number. Okay, but that's not right, because remember that when we're using these F statistics, we're thinking about the component of the variation explained by a certain part of the model. And here, the residuals here that's all the data, but that's not the independent observations we had for the hypothesis testing part, because we only had five per population. And so with a hierarchical model, what we want to do when calculating the F statistic is to use the mean squared of the next nesting level. And so instead of calculating our F by taking the mean squared, in this case population, divided by the mean squared error, what we're going to want to do instead is to calculate that by saying the F is going to be the mean squared of the population divided by the mean squared of family nested within population. Okay? And so we can go ahead and we can do this by hand. Again, this is not something that you would probably ever do, because as we'll see, there's much easier ways to do these things. But let's go ahead. Okay, so that still is going to be our mean squared for the effective population. And then what we can do is we can divide that by 276.72 divided by 16. So that's going to be the mean squared associated with this level. And so we go ahead and we do that. There is our new F statistic. And so now if we wanted to get the correct p-value for that, we would use what? We'd use the cumulative distribution function for an F. We'd give it the value, which is 12.22 something something something. Yeah. And then we, where am I? 3 and 16 degrees of freedom, lower dot tail equals false. That should, where are we here? And there we have it. There is the actual correct p-value. It's still significant. We would still reject the null, the null and accept the alternative. But you can see by staying honest with the number of degrees of freedom and being aware of how your experiment was set up, you can see that we went from a very high F value, 28.5, with a p-value of times 10 to the negative 12, to now a lower F ratio with the appropriate degrees of freedom. Although still significant, it certainly isn't times 10 to the negative 12. It's 0.0002. Still pretty small, but it's different. Okay, and so that's kind of a traditional classic approach to dealing with these types of hierarchical or nested models. And it's often, I'll point out when thinking about experimental design, it's often really tempting to say, oh, we're going to do this nested design because it's really, really powerful. And a lot of times the reason why it's really powerful is because the ANOVA is done incorrectly. In particular, it's because they're using the error mean squared as opposed to the mean squared at the appropriate hierarchical level. And so we really only have these 5 observations. We don't have 25 observations. If I were running this study and if I were designing this study, I would say, why don't we go to each of those 4 populations and randomly select one individual from 25 different plants, different families, instead of having it in this nested structure. Because we're doing a lot of work, but we're not getting nearly as much information. There are times when a nested design makes sense or when we have no choice but to do a nested design. But don't fall into the trap in thinking that it's a very powerful design, like it's some kind of a magical panacea, because it's really not. And we can prove to ourselves that we're not losing, we're just not accounting for all of this information in there. What I'm going to do is I'm going to create new data really quickly, just to kind of point out how this all looks. Okay, and what did I do here to make this new data? I'm using this function called aggregate. Aggregate is just a way that you can kind of summarize different parts of a data frame. What do I want it to aggregate? I want it to do something with seed mass, and I want to have family within population, and I want it to give me the mean. And then this is the data that I'm using. So basically what this is going to do is this is going to give me the mean for each family. And so here's, Northville family A, that's the mean of its seed mass. So that's the mean of those 5 values that were up here. So the mean, here's the raw data. The mean of those 5 numbers oh, this isn't me. I want ND. Where am I? There I am. The mean of those 5 numbers for family A, so 1922, 1911, 23, the mean for that is 19.02. So now that is the data. So remember, we started out with 100 rows of data. We felt as though, hey, we're going to have a lot of statistical power because we have that. But now I've just said, I don't care. I just want to take the average of that. So let's make a model where we just do that. So I'm going to just call it mod summary. No, mod mean. That makes more sense. Mod mean. And so this is going to be a model where we're just looking at the means. And so what I'm going to say is it's a linear model where what? Where seed mass is some function of population, and the data equals new dat. So now I have a model, and let's go ahead and do an ANOVA on that model, on that mod mean. And that's the answer to that, right? So this is when we just did it on the averages. We got rid of all of that extra information about all the within family variation. We just took the average for each family, and that became the response variable. What I want to point out is, first of all, we're getting the appropriate degrees of freedom, okay? We are getting the exact same F value that we got when we did it by hand, and we're also getting the exact same P value that we got when we did it by hand. And so this is just another way of just reminding ourselves that that's all nesting is. So it's not really often it would not be worth your while if you were to do this sampling design and say, we're going to take 5 families, but let's take 100 seeds from 5 families. Because at the end of the day, you still only have 5 experimental replicates. Okay, and so let's think about how to set this up as a mixed model, because it is 2020 after all, and for all the things that 2020 has become to us, one thing is true: we feel better about mixed models than we did 20 years ago. So we're going to use our friend, the library, I'm going to call in the Elmer test library, and so that's going to allow me to do the to set it up as a mixed model and be able to use, if we were doing a more complex model, we could use the step function or whatever. But I'm going to go ahead and let's make a model, and we're going to make a model using Elmer, so setting it up as a mixed model. And so it's going to be a mod. That mod is going to be an Elmer, where I'm going to have seed mass is some function of population. And now I'm going to add my random effects into the model. And what are those random effects going to be? The random effects are going to be each family. So we know that all of these pieces of information within family are not independent from one another, that it's only among families where there is independent information. So what we're going to do is we're going to allow each family to simply have its own intercept. And that's going to be the way that we're going to control for this nested by essentially what are we doing by doing that? We're treating family as a random effect. And it might make sense that you'd want to think about family as a random effect because they're just 5 families drawn from a potential distribution of families. So let's go ahead and let's set it up as we did before as a mixed model. So one pipe family, what that's doing is that's telling the Elmer function that we want each family to have its own intercept. And then our data is our nested data that we were playing with before. Okay, so now we have a mod. Okay, and we have parameter estimates for each population. And we can go ahead and do an ANOVA on our mod. Recall that when we load in the Elmer test package, if we use the lowercase ANOVA function, that function knows, since it's an Elmer object, it knows what it wants you to do with it. I don't know why they didn't at least do what car did, which was have a capital A versus a lowercase a. They could have done like maybe a ANOVA with a capital V. I don't know, but they didn't. So just be aware of that. So I'm going to go ahead and I'm calling up this ANOVA function. And we're going to look at the mod and look at that. That is the exact same answer that we got when, if we go back up here, when we did it on just the mean, right? Remember when we just took all of those values within each family and we just took the average of all those individuals? That is the exact same answer that we got when we did it that way. So here it is setting it up as a mixed model. Here it is doing it as a traditional linear model. But instead of including the error for family, we're just taking the summary of the family and going along, and just going away with it. So it's actually a lot easier to set it up that way. But we want to do things complicated because it makes us feel smart. And so we'll set it up as this type of a mixed model. Now, obviously, you could also have done the hypothesis testing a number of different ways, right? So we could do it as, I'm going to say mod reduced. And what I'm going to do is I'm going to say no population in there. And now if I used ANOVA, but I gave it 2 models, mod and mod reduced, now it's doing it as a likelihood ratio test, which we've also done before, right? So here you would say, yep, population is significant. Here's the p-value, okay? And then finally, the way that we could do it is to use the capital A ANOVA and put the name of our model in there. And then it's going to do that analysis of deviance, that other approach to doing likelihood ratio type statistics. Right. And so that's it for nested designs. They can get tricky. I often encourage people to really think hard if they truly think that they want to do a nested design. Because again, your unit of replication depends on what hierarchical level is relevant to your hypothesis testing. And since we were interested in their differences among populations, that means family was our level of replication. And we only had 5 observations from each of those 4 populations, as opposed to, even though we measured 25 things. So just be aware of that. But for the most part, yeah, that's it. Some places where nested designs are still frequently used are things like in quantitative genetics, when you're trying to estimate heritability and you're actually interested in the amount of variation within versus among families. And in those types of situations, a nested design might be appropriate. A lot of times you have no choice but to end up with a nested design just because of the reality of your experiment, right? If these were, these are seeds in principle, if there were only 5 trees in each of these populations, you wouldn't really have much of a choice but to take multiple samples, even though at the end you would only end up with 5. And so, again, the better experimental design here might be 1 seed from 25 different plants or 25 different families, as opposed to 5 from 5. Yeah. So, okay. So that is what nested designs are. The last one that we'll talk about next time is a variant of a nested design, and it's what's called repeated measures. It'll be very exciting. Okay. Have a good one. Stay healthy. Cheers.